Welcome back to Math 104. On a true-false exam with 5 questions, what is the probability of getting at least 4 answers correct just by guessing? When you go and list all the outcomes that are in the events, here they are, and there are 6 of them. How do you get at least 4 answers correct? You can have 5 right answers and 0 wrong, or you can have 4 right answers and 1 wrong, but that 1 wrong can be anywhere within the word. Before we started writing words containing 4 R's and 1 W, we could think that there are 5 locations where that 1 W could appear. Therefore, there's going to be a separate word for each possible location of that W. There will be 5 different words with 1 W and all the rest R's. This means that the probability we're looking for equals 6 over 32, which equals exactly 0.1875. This is not a tiny probability, but you still do not have a very good chance of getting at least 4 correct on this 5-question exam just by guessing. We go on to ask, about the same true-false exam with 5 questions, what is the probability of getting at least 3 answers correct? In other words, more than half the questions correct, just by guessing. By the same thought process, we need to count the number of 5-letter words consisting of 3 R's and 2 W's in whatever order. That corresponds to getting exactly 3 right. Or 4 R's and 1 W. That corresponds to getting exactly 4 right. Or 5 R's and 0 W's. That's for exactly 5 right. We just worked out that there are 5 words with 4 R's and 1 W, and only 1 word with 5 R's and 0 W's. The question is, how many have 3 R's and 2 W's? We would need to sum all of those up and divide by 32 to find the probability. Replacing this question mark with a number is something that we could do if we sat and wrote out all of these words. We could do that, but right now that seems a bit intimidating. If you sat down and tried doing it, it would at the very least be tedious. This question may persuade us that we need a better way to count words of specified length, with a specified number of R's and a specified number of W's for right and wrong. Or for that matter, we could just as easily have a question about T's and F's, or H's and T's in another context. Our next task is going to be the very important one of developing a systematic way of answering this question, of counting how many words there are of a certain type. To develop this systematic way of counting words, we're going to work with a new example, and this is going to be our guiding example for the next little while. We're still talking about experiments with multiple stages and only 2 possibilities at every stage. Now we're going to start at the top of this hexagonal grid in this cell right here, and we're going to walk downwards from one cell to another cell, but we're going to randomly move either left or right at each downward step. Each randomly selected downward path through this grid is going to be represented as a sequence of L's and R's for lefts and rights. This path right here is represented by the word LRRL. It is the path left, right, right, left that took us on exactly this route. But there are many paths, such as left, 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 right. That's also a path, and it ends up in a different place. Now let's focus one cell at a time. Now let's focus on one cell at a time, and for each cell in the grid, let's label the cell with the paths leading down to it, and count how many paths there are. So from the starting point down to this path, from the starting point down to this cell right here, there is only one path. There is only one way to get there, and that is the path go left. So there's only one of those. To this cell, there is only one path, and that is the path go right. There's only one. This row that we just filled in, we are going to call row 1. You might have thought that we would call this row 1. We are actually going to think of this as row 0, because while we stand here, we have taken 0 steps. By the time we get to this location, to this row, we have taken 1 step, whether it was to the left or to the right. We continue. In this grid, in this cell, there's only one word LL, because the only way of getting here is by going left and then going left again. So there is only one path that leads from the that leads from the top of the grid to this cell, but something interesting starts to happen in this cell right here. You can get here by two different paths. You can arrive by way of this cell, which means starting out going left, but then going right to get here, or you can arrive at this cell by starting out, going to the right, and then going left. This method is systematically enumerating for us what the two-letter words are, and it's counting how many there are that land in the same location, with a certain number of L's and R's. Right here we've just written out all the two-letter words with one L and one R. In this last cell of row 2, we have RR. There's only one way of getting from the top of the grid down to this location. So that was row 2. For each location in row 3, we can write down all the words that lead from the top of the grid to that location. We can also find the number of paths that lead from the top of the grid down to that location. And in so doing, we're going to find the number of words that have a certain number of L's and a certain number of R's. Another observation is that even if we didn't write down the words themselves, we could still count how many paths lead down to each cell. For example, once I've reasoned out that there's only one way to get here and one way to get there, I can reason that the only way to get to this location in the middle of row 2 is that there is one path coming from here in row 1, and there's another one path coming from there in row 1. If I add up this one to that one, I find out that there are two paths that lead to the middle of row 2. I can only have arrived via the left location in row 1 or via the right location in row 1. Before going on to the next video, fill in row 4 in the way that we've done for rows 1 through 3. In each cell in row 4, list all the words that correspond to paths that lead from the top of the grid down to that cell, and indicate how many of them there are.